How are we doing AP Statistics? We're going to be finishing Chapter 4 by talking about two things that we'll be seeing in much greater detail as the year progresses. First, randomization. Then we're going to be talking about data transformations, right? So randomization and transforming sets of data without corrupting them. Okay, so first we're going to talk about randomization. So as we've seen before, the summer months are the ones that have the lowest average wind speeds in Hopkins Memorial Forest. We see this time plot over here that seems to say as much. In the summer, that's in this region right here, this stretch of time, we have some of the slowest wind speeds. So here's our time plot, and it displays the average wind speed each day of the year. Okay, so we got our winter, and then our spring, and then summer, things really slow down, autumn, and then winter again, things pick up. Okay, so the big question is, how can we tell that this is not just a fluke? How can we tell that there is actually a trend? So one way to confirm, as much as we're able at this point in the year, the summer months truly do feature slower wind speeds. And this is not just a fluke. This is not just something that if we were to do the same procedure the next year, find the average wind speed of each day, that the summer would be not unnaturally slow in its wind speeds. One way to check to make sure this is legit and this trend that we're seeing is real is to randomize the days of the year a few times and see if we erase this trough that we see. All right, so if we put the days of the year in a random order, does a trough just kind of naturally appear in the data? And the trough just so happened to appear in the summer months here, but if we reorganize the data, a trough would appear somewhere else, and the trend is a big nothing burger. Or is what we are seeing over here actually a true trend? Okay, so since the reordered time plots seem to erase the troughs, all right, so we reordered the days of the year, put the days of the year in a random order, and look at that, we have no trough, all right? This looks like chaos all the way through. The lower wind speeds in the summer are not a fluke or a coincidence, okay? If they were a fluke or a coincidence, then we could reorder the days and we would coincidentally get a trough somewhere else, but that does not happen. We can keep doing this, it will not happen, okay? So that trough that we see here is legit, all right? Putting the days of the year in proper order yields a meaningful result, and we should take it seriously. All right, now we're going to talk about re-expressing or transforming data to improve symmetry. Okay. Personally, this is among my favorite things we do in statistics. I think it is so cool. So if I nerd out about transforming data, re-expressing data a little bit too much, forgive me. I think this is one of the coolest things you can do in statistics. All right. So recall that the mean and standard deviation have the most applications in statistics. That is an understatement. They have by far the most applications for any measure of center and spread. All right? We should not use those metrics, however, for heavily skewed data. The mean and standard deviation are not appropriate measures of center and spread, respectively, for data that look like this and like this. These are the same sets of data, by the way. So we're considering the graphs to the right and note the number of outliers. Oh my goodness, I feel like there's a bajillion of them out here, right? Perhaps the scale can be adjusted, specifically the scale of the x-axis, not the frequency, the scale of the x-axis, so that the data are more symmetrical. Now, mind you, we are not going to corrupt the data. We are not going to pulverize this graph into a bell curve looking thing by cheating with the numbers. No, that is not what we are doing, all right? We are going to apply the same function to each value that our variable compensation gives us, right? We're going to apply the same function throughout. And if we do that properly, if we use a good function, we can take all these data values and make them into a bell-shaped like curve. It's really cool. And we will go very far in depth in this in chapter 9, all right? But we're just looking at the basics right now. All right, so we can apply a function to each data value, and that will adjust the scale of the x-axis and improve symmetry. Okay? We'll find throughout the year that though this process does seem to obscure data, our graph looks a little different. The skewness disappears. That's by design. Symmetry makes data easier to interpret since we can use mean and standard deviation. Okay? So there is a proper way of doing this without corrupting our data, and that is one of the things we'll talk about very much so in Chapter 9, but we start the discussion here in Chapter 4. All right, here we go. So if we apply the log function to each data value, we acquire a more symmetrical graph. So here's my original graph, and here is my graph in which every compensation in millions of dollars, we took the log of it, all right? And look at that, this right skew curve turns into something that looks like a bell curve with a couple of outliers. Okay, fine. But there are significantly fewer outliers. Everything over here is an outlier, right? Even some of these guys are outliers, right? Here we have 1, 2, 3, maybe 4, 5, less than up here, all right? And the bell shape is much more agreeable. So for example, it's easy to see that the re-expressed graph, in the re-expressed graph that is, that most of the data are between 2 million and 63 million. All right, that would be very hard to tell in this graph. But looking here, we can see the vast majority of data values are between 2 million and 63 million. Now, how on earth am I able to say that, all right? That's because the x-axis is the log of the compensation, all right? What we see in this graph is that most of the data are between 6.3 and 7.8, right? Well, log of $2 million is 6.3. And log of 63 million is about 7.8, right? You can see that the log function takes a big number and makes a little number. So we work backwards, and we'll talk more about how to do this later on. But we can just look at this graph here, see where most of our data lie, and work backwards, all right? 6.3 corresponds to $2 million. 7.8 corresponds to $63 million, right? Would you be able to tell that looking at this graph? I wouldn't. I see this massive clump of data right here that kind of fades after $50 million with a couple of values over here. And I don't know what to make of these small values over here. Are some of these CEOs not making any money? All right, it's really hard to tell in the initial graph, but the log graph really does clear things up. Right? There are still outliers, okay? There are a few outliers in the log graph. I agree. Sometimes you can only do so well. But they are no longer as exaggerated as before. We don't have the bulk of our data over here and this fella here out in no man's land, okay? We have outliers, but they're not terribly far away from the bulk of the data, right? And nonetheless, we still may have a high outlier, which is really amazing because logs have a tendency to take big numbers and make them small, and really big numbers and make them almost as small. Think about what a log does. Log is log base 10. This says 10 to what power is 2 million? Well, the answer to that question is way less than 2 million. 10 to the what power is 63 million? Well, that number is way less than 63 million. Okay? Log takes big numbers and makes them small, and takes really big numbers and makes them almost as small. That's the value of using log for data transformation. And still, this might be a high outlier, which gives you an idea about how absurdly rich this CEO must be. All right. I love this example. This is a great example. Okay? Re-expressing, transforming data to equalize spread across groups. Okay? This is a situation in which data re-expression is absolutely essential, or else this graph and these data are useless. Okay? This is a wonderful example from our textbook, and here we go. The graph to the right shows the concentration of cotinine. So that's a byproduct when the body metabolizes nicotine, all right? And that's measured in nanograms per milliliter, all right? Formalities. We got to talk about what this thing is. All right, in smokers, non-smokers who are exposed to smoke, all right, so secondhand smoke, and non-smokers not exposed to smoke, all right, so no ETS. That's what those things mean. And we have the smokers right here who seem to have reasonably understandable data with a few outliers. And then we have these, I guess they're box and whisker plots, but they're just whiskers and outliers. What's the deal? So clearly smokers have the highest median concentration of cotinine and by far the greatest spread. Okay, that's easy to tell. But what's harder to tell with this graph? Well, what's the meaningful difference between these two in terms of their spread? All right, barring the outliers, no ETS and ETS, their spread looks virtually non-existent. Okay? How can you tell the difference in spread between these two groups? Okay, ETS is a little bit higher. The median is a little bit higher. Fine. What's the spread of these two sets like? How can we compare the spread of these two sets of data? You can't, right? Completely impossible. All right. Now, before I get too far into this, I'm going to anticipate a question. How can you have a score of -1? Well, if a logarithm has an input of a value that is greater than 0 or less than 1, you can check this on a calculator. If the input of a logarithm, like common log that we see here, log base 10, if the input of that log is between 0 and 1, not including 0 and not including 1, your output is a negative number. Okay? So we have these negative values here because we're using a logarithmic scale. Okay? Hopefully that clears things up. Cool. We have not destroyed our data here. We have not produced ridiculous results that we need to hold under scrutiny. No, this is a feature of the logarithm function. Okay, great. So that's out of the way. Let's see how this works. Log is a useful function to apply to the axis of cotinine concentration since data values cannot be negative and are skewed to the right. Okay, so data values cannot be negative. All right, why is this important? Logarithms cannot receive negative inputs, okay? So if you're dealing with data that has negative numbers, by the way, that is extremely rare in this class, extremely rare. But if you have data that can assume negative values, the logarithm is an inappropriate way of re-expressing data. Logs cannot receive negative inputs. So yeah, don't want to do that. Now we can see that the spread of ETS is greater than the spread of no ETS. Cool. This would be impossible to see without employing the log function, right? So we see no ETS and ETS, very good. We have, clearly there's more spread, and a detail that you may have noticed is that with ETS, we no longer have outliers. Data re-expression, that is awesome. Sometimes we can even get rid of outliers and make our data speak even more clearly, right? We don't have this noise out here taking away from the bulk of what is happening. We don't have the noise out here taking away from the bulk of what is happening. Really cool. Data re-expression, awesome stuff. And there's your homework. Also awesome stuff. Have fun.